Hi everyone, today we do Cambridge A-Level Further Maths Paper 2, which is the Pure Maths 2 paper. The syllabus code for this is 9231 for Further Mathematics. This is variant 1 of paper 2 from the May June 2025 series. Okay, now we go for question 7. Okay, question 7 is a differential equation given you in this form, and they also given you some boundary condition, and they want us to give the answer in the exact form. So previous question, in question 6, we dealt with a second order differential equation. In this case, it's a first order and it's a linear differential equation. So linear equation, what it means is that it can be presented in this form, where you have a dy dx, you have a function, then dy, and then you have equal to another function. Right, so this is what we call a linear function. And in this case, the function attached to the dependent variable is is px, which is this rational function. So the solutions to this type of equation is we need to use what is called an integrating factor. Integrating factor is this one. We have a mu x equals to e to the power of the integral of px in respect to x. So this one will be our integrating factor, for which after we have this integrating factor, we multiply the entire equation on both sides with the integrating factor. And if you notice, you can try and expand on this side, on the left hand side. And we notice a pattern here where it looks like the result of a product rule. Right? It looks like something multiplies something and you took the derivative, then in this form it came out. So what I can tell you is that it's actually exactly it is the product rule of when we take the derivative of the uh, the integrating factor multiplied by the y, the independent variable. So we leave the integrating factor, leave that alone, then we differentiate y, you get dy dx. Then we differentiate the integrating factor, what we get, because it's a e power of the integral px, right? So uh to 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 differentiate an exponential function, you just leave it. Okay, you just leave the mu x, but we need to take the derivative of the inside function, which is the power, and multiply by the derivative of that. So the derivative of an integral is just the integrand, which is px, and then of course we leave the y. So the solution to this, or the solution to a linear ODE, there will be we know that the derivative of the integrating factor multiplied by the independent variable will be equal to the integrating factor multiplied by whatever function is on the right hand side. And to integrate, you just have to just integrate both sides in terms of x and also the integrating factor and y. So first of all, let's identify our px. Right? Our px in this case already we know, and so we want to take the integral of px. If you've done your practice of integrals, it looks like something where you have a derivative of the function on top and the original function on the bottom. So we'll go ahead and use a u substitution. So we'll let u, which is arbitrary function, u in terms of x, function of x, to be the bottom, right, the bottom function, and therefore we have du to be 2x plus 10 dx, and I can isolate dx to be du over 2 of x plus 5. I'll factor out the 2, so it's easier to see later how we're gonna use this to integrate. So now we're gonna replace everything back into our integrand. So the x plus 5, I'll remain it first, and on the bottom, this quadratic expression is just u. Okay, we set it to be u already. And dx, I'm also gonna replace it as du over 2x plus 5. So this x plus 5, that's why I write it like that. It's easier to see that it cancels. And also this 1 over 2, that is just a scalar or constant multiple. So I'll bring it out of the integral and we'll have du over u. Right, so du over u is just the natural log of u. And u, again, that is the quadratic expression, so I'll just rewrite it as such. Okay, because we're also gonna raise, okay, for our integrating factor, we're gonna raise it to the power of this. So I'm also going to move this negative 1 over 2 using the rule of natural log. I'm gonna move it up to the power. So power of negative half, just gonna be a 1 over square root. And therefore, our integrating factor mu of x is e to the power of ln 1 over square root of the quadratic. And therefore, it just cancels out to become 1 over square root of the quadratic. At this point, for this integral, we don't really need to worry about the arbitrary constant because this is just the dummy integral. Okay, then we can just proceed to the next step, which is now that we have our integrating factor, we're going to multiply both sides by an integrating factor equals to, on the right hand side is just 1. So it's 1 multiplied by that function will just be 1 over this one. Okay, on the right hand side, I can straight away simplify this to be what I've proven just now, right? It's just the product rule of the integrating factor with y. So this entire left hand side, that will be just the derivative of y over the integrating factor. Okay. The one in red, remember the one in red is our integrating factor. And then on the right hand side, maybe what we can do is we can complete the square for this quadratic expression here. So do that very quickly, you should be able to get. Okay, and then now I want to integrate both sides. So on my left hand side, I will get the differential of y over the, or y multiplied by the uh, integrating factor, and on the right side I can integrate with respect to x. And perhaps also this 36, if you try and simplify this even further, this is a 6 squared. And since 6 squared is here, I want to pull it out, because I want to pull it out of the square root, because if I have the formula sheet here, we look at the formula sheet for integration. In this form, we can integrate it to become the inverse hyperbolic sine function. So I want to make the plus 1, I want to make it into plus 1 instead of plus 6 squared. So I will divide, okay, I will divide the entire inside of the square root by 6 squared. So which means I will get the 6 squared, I can take it out because it's just a multiple, and I will get this expression plus 1. Okay, and then here I can do another substitution for my integration to be, let's say we let v be x plus 5 over 6. So dv be 1 over 6 dx. So 1 over 6 dx, you can see here, you can replace that with dv straight away. So dv, and we have the integral over this expression. That's our v, so I'll write v squared. Then we have a square root plus 1. So on the right hand side, the integral and the differential cancels out, and you'll just have a y over our integrating factor again. And on this side, right, we've already, we look at the formula sheet, right? It's exactly the same form as this. So it's just a hyperbolic inverse of the sine function. And in terms of v, so v, I can directly replace it to be v, I can directly replace it back to be x plus x plus 5 over 6, right? That's what we set in the first place. So x plus 5 over 6. And we're not done here because we have done this integral, but now we have to add the arbitrary constant because this is an indefinite integral and we are given some boundary conditions here. Y0 x equals to 3. So let's start on the next page. Y0 equals to 3. So yeah, we substitute y equals to 0. So this entire term on the uh, on the left hand side goes to 0 actually, and on the right hand side the inverse hyperbolic sign, x is 3, so 8 over 6 plus 6 plus c, so our arbitrary constant goes to become negative inverse sine 8 over 6 or 4 over 3. Now that we have the arbitrary constant, we can go ahead and use, okay, because they want it in the exact value form, we can use the identity given to us in the formula sheet, that the inverse hyperbolic sign will be the natural log of yeah, that one. So I'm just gonna write it down, and this will come down to negative ln3. And so in total we can just rewrite our function y over the integrating factor. Yes, and then we can go ahead even simplify even more. We can write y of x, it will be this entire thing, and we multiplied it by the square root. So we get exactly y as a function of x. Just yeah. So yeah, this should be the exact, right, the exact function of the y. Okay, so that's how you solve the linear first order differential equation.